Welcome everyone to another nightly live stream. I wanted to share you some update with our FPGA fun that we had here with this icebreaker FPGA. By the way, there's no, this isn't. Anyway, if you're new to this channel, we do here various low-level stuff, including recently this FPGA from 1-bit squared. Here's some crowdfunding project. Actually, it doesn't make so much the most sense to have this small view here. You get the idea. And we started already to implement some video core, as you need to do everything, or what need you can do everything yourself there with all the logic elements or the logic gates. And in previous videos we have done graphic mode, and graphic mode was relatively easy, or easy, but mostly just piping here all the pixels out on the pixel clock here, and like one-to-one. I have here also some overview now, which is here. So we are targeting, so the issue is that this is a relatively small FPGA, but certainly enough for us and you at home to do some first tests. So we are dealing with some 5,280 logic cells and at least thankfully 1 Mbit single port memory plus some 120K dual port memory. And the issue, of course, is we also have from Clifford Wolf here Pico RISC-V. So what we are actually up to is implementing some small homebrew microcomputer system, and we cannot use all of them. So if we would use all of those logic elements and memory, we could do some relatively nice graphic, but the issue is we need most of those for our RISC-V core, for Pico RISC-V core from Clifford Wolf, and that you can just use the open source, formally verified, amazing stuff. And we need, so what was it? So quite some, I think, was it 4,000 or 3,800 as far as I remember, for the Pico RISC-V, and most of this memory when we want to run C programs and write games and software, we need most of this memory, like the single port memory here, is used by the Pico RISC-V, leaving us with 120 kbit of dual port block memory. And even this we cannot use all, because maybe we want to have some sound and maybe PS2 keyboard and audio, so we always need a little bit memory here and there. So anyway, so the summary is graphic mode. I was targeting here some 320 by 200 something, and in text mode with 8 by 16 characters, that makes some 80 by 30 VGA text mode kind of something, so that is 7K plus a font. And we had all of this working already in previous live streams. Welcome everyone, Diethard and everyone else. So yeah, we had some text mode was surprisingly, or you would think text mode is simpler, but the issue is graphic mode is each of those single pixels, like each pixel here memory address, each pixel here equals one memory address, and you basically nearly only need to stream this out with a pixel clock to the analog or digital HDMI DVI transmitter. And in text mode we have, although it programmatically sounds so much simpler to have one character like T, ABC and so on, of course for each of those, so 16 by 8 pixels here are 2 memory addresses for the text character and color attribute, and plus a character. So it's actually much more complex operation than just one-to-one streaming out there some pixel. And by the way, sorry for the capture quality. This is also why I don't have camera right now. This is with this Chinese 80 euro HDMI capture thing. On the display, this text is much sharper. This is just there you see the capturing dongle. Also, I think it's probably jittering a little bit. Maybe this, we had this in the previous videos, video signal. I'm using others people video cores there, and that is still not syncing perfectly. Even without this capture, this was still off. So, but I first wanted to get some more features done, because features are more fun to do than looking for the last jittering and video signal. Also, these characters, you see the characters also improved a little bit. The characters, because the issue is, as we established in previous videos, is memory access time. We need, for each of those pixels, we need to load for memory access the memory, the text character plus the color attribute. We are combining this to a 16. I made a video why 16-bit loads, like one 16-bit load, is much more amazing than two 8-bit loads, because it's one access cycle instead of addressing two different cells or something like that. Plus video memory. This is also why initially I thought we can combine this here in our addressing space. Let me just, how should we position this? Something like that, I guess. I hope it's somewhat readable. But I figured it's better for us to have two memory areas, because these are blocks. So these are like 6 or something, 20K blocks or something. And this is why it's beneficial for us to have the font here separately, and we will also most likely keep it like this. So I improved this here a little bit, as you can see. This is, except the video capture, which is, anyway. I implemented two, so beside fixing this memory access cycling stuff here, I now try to preload on every 2 and 4 pixel. I preload the next character. It's making it a little bit better, but not yet perfect. We need to further work on this another day. But this is probably a couple of days of research, of learning Verilog and stuff. So I thought it's much nicer and cooler to implement some features. So features I implemented. Previously, you see this blinking. So I now implemented the VGA compatible blinking attributes. This is just very few lines of code. I'll show you this in a second. In Verilog, again, this is we program all the logic gates here. And the other thing is I made the palette user definable. Previously we had this hard coded here in the code, and now I show you this in a second how I did this. So this was surprisingly simple. I think it works fully. This has a benefit if we really do some vintage graphic gaming stuff without a redefinable palette. The 16 standard VGA colors would be really ugly, because it's just like totally bright and shaded red, green, blue, yellow, brown, black and white and gray. And this is already quite a bit limited. So at least making this user definable allows to optimize the color, look and feel of any potential Tetris or Fogger or whatever game we might do. So address map, I also typed out here some address map. Also coming next sometime soon, maybe in a week or two, maybe for Christmas, interfacing this with the PicoRISC 5 core. Right now it's running freestanding. That should be relatively simple. Memory map, I probably still try to target 320 by 240, although this really stretches the memory requirements quite a bit. And addressing wise, this will be like the whole frame buffer addressable for either pixels or text mode. And then we have here, so this is what I typed here, address map 32K something frame buffer, either pixels or text. And then after the end, like how you usually do it, often done with NVIDIA ATI graphics, first the frame buffer and at the end some control stuff like palette cursor. I actually most likely maybe next week or so I implement cursor. So I'm in the meantime considering I most likely will implement a hardware cursor, because why the freak not? So coming to the code here, this is Verilog, looks C-like, but yeah. This still gives me a warning. Also, yeah, indentation, the original indentation was different from what Emacs wants to do here. This is our video signal, and we are anyway limited. So this FPGA PMOD stuff is anyway, due to pin limitations, only outputting 4-bit. So we only have 12-bit in total anyway, but we have 16 colors anyway, so it doesn't matter for us at all. So to make this easier, you can actually define wires and assign registers. So just for my own code, because this video core that I sourced was using this video RGB stuff and I wanted to assign it sometimes in one assignment. This appears to work but gives me a warning. Maybe we can take a look at this later. So what this does is you can define just multiple wires and connect them. So this is just like an alias. We connect this, we assign this here, this wire video RGB, connecting this wire directly to the video RGB registers here, to make my life a little bit easier. Also, what is new, we use this frame counter, so we count the frames, the video frames that we output, because we need this for the blinking attribute. And here, this is the old code, just some hello world, just a character. We load this character set from the file, and this is now our new palette. Previously, I had this hard coded, and actually this palette, because you could do this in memory, but we don't have so much memory, and so I just, just wanted so much to checking what I'm showing, and then this actually consumes quite some logic gates, and in total the new code, so I was at 150 logic elements or something, I'm now at 200 something. So this register, so I define here 16 registers for palette. I'm intentionally not using memory because memory would be too wasteful, so I figured for our flexible user-definable palette, just use some freaking registers, don't need memory for this, just meaning some like buffer elements that act as registers there in the FPGA. Although this is a little bit wasteful, and actually if we wanted, because we waste or like we consume 16 times 24-bit register, and of course you see here are the patterns. This is directly the black, blue, green, cyan, red, magenta, brown, light gray, light black, aka dark gray, light blue, light green, like cyan, light red, light magenta, yellow, white, standard VGA palette. And this is just the initialization. So later, when we connect this to the RISC-V core, we can write any new value in there, so making this user definable and so on. We could, do we have comments in the audience? Let's see. Also, when I should have used, this is why I usually use another browser, because when I go over there. Anyway, do we have comments? What if emulator something? Did I accidentally like the jitter a lot? Reminds me of a composite video with bad V-hold, but would get annoying to work with. Yeah, so the last time I used it on a real display, it wasn't as jittery there. So comments in the audience, not directly to that. So the way we could actually vastly, if we later run short in logic elements for the sound output, because ideally I want to attach some keyboard, most likely PS2, maybe even if we go super fancy, maybe if we are lucky we get USB onto that. But let's see, another day there is already someone else has done USB on this icebreaker, I think. So the way we could drastically reduce this is we don't even have 24-bit, right? We only have 4 bits, so we could make this 12 bits or something, because our FPGA hardware PMOD output here only has this HDMI output, because it simply doesn't have enough pins here, right? So because it's using these pins, there are only 4 pins here, 4 pins here, 4 pins here. This is why it is limited to 12 bits in total, 4 bit per color, and not a big deal for our homebrew stuff here. So we could theoretically at the end, to make this a little bit less readable and actually half this bits here. I'm not sure if Yosys would combine this. Theoretically, you could probably combine this. We could also, with combining, I mean combining here multiple defined registers in one logic element. I would guess Yosys is as sophisticated to maybe potentially do this. But if it doesn't do this, we could do this manually. But again, only it makes everything a little bit less readable. So for now, I waste all those bits there, so whatever. This is our video core. Another day I need to make this even more readable. I moved this all. Previously I had this in a dedicated define here, but because I was tinkering with this pixel shift there of memory load delay. I was moving this all in this always on positive edge pixel clock signal here. You see this is the code that I based upon. This is, by the way, from Elizabeth Scott, aka Scamline. And yeah, we still need to compensate for this memory access. So I do this, by the way, I do this here text mode preload every 8 pixels. I preload here on X position 2 because we only need to load it from memory every 8 pixels, but somehow this still has a delay. So we still have a little bit of delay because anyway, so this is, I now have a next character, a next attribute, but this does not yet fix the problem entirely. If you are an FPGA expert, feel free to give me a tip how to best work with this. Otherwise, I will also soon publish this code on GitHub. Previously, if you compare this, if you want to see all the details, the previous video, previously I had here hard-coded the hard-coded assignment of this VGA palette. Now we load this into only this bits in this foreground, background color and blink attribute. Here the 7th bit is blink attribute. This is also new since yesterday night. So just 1 bit. And this is just some, this is just some test pattern you can ignore. This was just for testing here, timing testing here. And the benefit of this is previously we only had the palette for the text mode. The new thing is I still need to test it here somewhere of this sort here for the graphic mode, not yet tested the graphic mode again. But the benefit of this is also this should not be rosin, this should be something like probably foreground color, I would say. The benefit of this new code is that it would make this VRAM frame buffer load go through the palette lookup if we use it like this, because the palette lookup now is here, and this is now coded like this because we need to case on the color. Actually, wait a second. This means text mode. Here's, by the way, I position whatever okay, so much to that. Need to check the graphic mode is whatever. Graphic mode is not finished with the palette port. So here we switch on the color and then just assign here. This is like basically a multiplexer of assigning the palette register to the video RGB output. And again, the benefit is now also that this would theoretically allow us to have palette lookup for frame buffer, and the blink attribute is, by the way, here. So previously this was text mode. Here's our if text mode, and the mask is our text character set, and the blinking is as simple here as this. This is the whole code needed for blinking, except assigning the blinking 1-bit blinking register here. So blinking on text mode as simple as 1-bit load here, attribute 7th bit, and then on drawing the text character here, whether to paint it. So previously we painted the foreground or background color based on the mask of the bit mask of the this is here just in 1, so this is just in fancy 1 pattern that we shift down by the X position. So this is the X position we are drawing right now, and this is the row of the, so this is just masking here the 1 to the right position of the X position, and this is the text, the row of the text character we want to display. And either we paint the foreground or the background color, and blinking is as simple as only painting the foreground color if it is masked. So if the bit is set in the text font, and blinking either if not blinking or if the frame is divisible by, I used here 16 or 32, maybe 32. Probably, let's see, we can double check that. Pretty elegant and simple. So 1, 2, 3. So not sure, something we can. So that would be 1, 2, 4, 16. So maybe it's 32. Maybe with the 60 Hz refresh rate, this makes it blinking every, it looks elegant and useful to me there. This timing looks quite nice. So yeah, this is blinking, super simple and palette now. And next I need to, well, I will most likely fix this off by 1 or 2 pixel stuff here. Or actually the whole video signal is shifted, so this is actually the 3rd and 4th row, I think. So you see here some pixels are not visible. Unfortunately, as per the previous videos, you can see all the glory details there. But next, as usual, this is a fun project. And for the fun, of course, it's the most fun to actually do new features. So next I will fix the frame buffer mode to work again for colors. And then this should be just some 30 minutes or so. And then I will finally marry this here and integrate this to the RISC-V stuff from Clifford to have this addressable by RISC assembly, machine language or C code, and allow us to do some fancy, hopefully fancy, Lua programming, basic Lua, whatever we would want to program. And I hope you find this interesting and learn something from this stuff. I for sure, even for me, I've only done this a little bit at university, and of course my hardware reverse engineering, but reverse engineering others people stuff, either PS3, SGI or scanners for our exact scan, is something else than writing it from scratch, like this memory access timing and all the other palette lookup stuff, all the details you and interfacing this here with, and interfacing most likely will be as simple as we will get some wires from the RISC-V core and we will just have some code. This will be super simple. This will be some on positive edge of memory address and then comparing the read and write address from the RISC-V core, and then if this address is our frame buffer or palette, then assign it here to the VRAM or palette registers. That should be relatively straightforward. The only issue is that I said it before in the previous videos that when I combine this, so it's compiling or synthesizing, and the only issue is that somehow I have not yet integrated correctly, so it doesn't give an error and it like fully synthesizes, but it optimizes it away, so it somehow looks like I didn't connect in my other module. I showed this already on some other video. This is how you integrate this. You have your RISC-V core, another file, and then you have here in the RISC-V core, in the Pico RISC-V, for example, from Clifford Wolf, you would reference, I've done this, I show you in the next video, next weekend or so. You assign here some signals, but somehow users optimized it away, so not yet really sure. I did it similar. There is a UART, a serial UART. I did it similar to what example code was in there, just that my code gets optimized away. So clearly there's some definition. All right, I think, now that I think about this, the issue was that actually it gives me a warning that this output signals are undefined, although they are in the scheme file of schematic file. So whatever is going on with this. So maybe it's only optimized away because it doesn't have the outputs that they are in the file. It's just the software and hardware development being difficult, and although you see stuff, it's not doing what you think it does. Anyway, I hope you enjoyed this fun little update here. I'm at least pretty satisfied with my blinking characters there, and so the palette looks to be working. Actually, the palette should be working because initially I had it reversed and the colors were reversed, so we could actually test this if we wanted to go to the palette, for example, palette here. For example, we could make black also for a quick test white. Of course, later this should be software controllable. So make, and I didn't even show you this. This is how it looked. There now we synthesize this, so I made here this palette all bits FF, and let's see, yeah, that even worked. So yeah, tested here live on YouTube, didn't even test this before, I only naturally, why I knew it was inverted previously, because I had this is why I simply inverted this somewhere. Where was it? RGB, I think it was here. This is why previously I had the RGB. This is why this order is. Do I even show it? No, I don't show it. The order here, this is why previously I had red, green and blue switched here in this defined. Anyway, I find this pretty satisfying. Definitely something new. You see also here, this is loaded, maybe this is loaded off by one also. So yeah, still some memory access required, but yeah, we are still live. Welcome there, unexpected maker. So I find this, I honestly, for me, this is really relaxing. I can only recommend it for you if you want to bored with software development. What do I even show here? If you're bored with software development, want to do something else, which by the way, we probably want to resynthesize. This is light color. It's slightly... I also wonder, when we take a look on this picture, that I'm not really sure if we get a full white. That would be a little bit disappointment with this 4 bits. Maybe with this lower 4 bits are always 0. Maybe we don't get a full white then, but these are small technical stuff. Anyway, I find this super satisfying, super interesting. I can only recommend to others to, especially instead of wasting time and playing games, which of course also sometimes is fun and even done on this channel, but otherwise do some stuff that you usually don't do, either hardware if you don't do software, or something entirely different like playing an instrument, guitar, drums, you name it. Super fun in my opinion, and in general much better than again, games and stuff. Even while traveling, you can even travel with this stuff here. Super small PCB, just one serial USB wire. Let's see more comments in the audience. Mr. Bonk with his sax machine and his emulator. It's my own emulation there, runs 120 something MIPS. So today we had text mode stuff, blinking attributes, user-defined palette. Also, because I actually have done rendition verite cursor, so software cursor should not be too difficult, and software cursor, so this will mean, of course, we will not have a huge cursor because we don't have so much logic elements and memory left, but the cursor, we will do the same as a palette, so the cursor will be, where do I even have it? So the cursor will be some 16 by 16, I think I was thinking. So this will be, yeah, this will be 16 32-bit registers for 16 by 16 pixel with 2 planes for transparency and color. And we should have, so this is exactly the same or similar size to the palette. And I think this should be doable. So sometime soon, so next I will do cursor, graphic mode, and then wire this. Also I didn't show this because, yeah. So yeah, 16 by 16 here, and it will be in 2 planes. Here 16, similar to the palette there, 16 cursor registers, 32 bits for 16 by 16 pixels, and then transparent inverted, so 0, 0, transparent, 0, 0, because we have 2 planes, right? 2 bits per pixel in 2 planes in plain speech. And then, so the high bit 0, transparent or inverted, and the high bit set then color 0 or 1, also of course user definable. They are similar to the palette. I will do this sometime soon, and then the integration. And again, if you have any tips to this, if you are much more in Verilog and FPGA profession or something, feel free to send any tips my way. Let's see, reference platform to the end of the stream. breaking, sitting in a box, waiting for some free time, unexpected maker, cool stuff. I will also upload this code to, also probably should close this, that you see this more often. So I will upload this. Well, right now this code is not the most amazing, but yeah, also some video timing stuff to fix. But anyway, I will soon publish it to YouTube, and maybe we can, we most likely will really over the next months. You see, I'm already made some progress, already looking pretty promising. So only so if I would work day and night, if I would work every day, probably 1 month of work I expect of integrating this with the RISC-V core, finishing the video stuff in all its bit precision, and then adding keyboard, and I don't know if maybe we are really super lucky to get USB into there. That would be certainly super amazing. And then, of course, yeah, right, last but not least, we need to get some pulse with modulation of some sound output. Yeah, so this is Unexpected Maker. Yeah, this is running on the, I don't have a camera here right now because I have, yeah, but previous videos. What do you mean with PC impulse code modulation? We will see how much audio we will get on there. I'm already happy when we get something beeping. So most likely at least some beeping sound with 2, 3, or 4 voices. And I'm not sure if we will get so lucky that we have so many, because I would do pulse width modulation stuff of, yeah, digitally sampled audio, but the problem is we don't have so many logic elements left. We have here logic elements right now with only the video core is 219, 4%, but yeah, in memory, this memory, 80% of the memory, so most of that, unfortunately. But yeah, let's see how much. And this other single port memory will be used by the RISC-V core, so all of this, sorry for the scrolling, some output of something. So all of this memory will be used by the RISC-V core. So yeah, let's see what we have left. But we have some SPI I2C stuff, so we will hook up there something. Anyway, do we even, I showed this, good. So yeah, I hope you learned something. Electron Ash is trying to get some Z80 ROM for the Sega Nami meat chip running on the trusty old D1. Nice stuff. Yeah, nice for tuning in. Hope you learned something. Most likely, hopefully, that Verilog and FPGA is cool and fun, but difficult nonetheless, and probably that neither or software and hardware is difficult, and yeah, especially getting all the timing bits and stuff right, and more testing, and all the fine details. Anyway, I had some fun. I hope you learned something and we make some progress. And leave me in the comments below. Of course, I'm a little bit biased, but I would find this probably... Anyway, I think this should be more powerful than the 8-bit Sky Commodore something, X16 something thing, and certainly more modern with RISC-V. So I think our CPU should be faster. Not sure where we get with sprites, but in my opinion, this is somewhat more fun because we do the hardware completely ourselves, and the RISC-V CPU should most likely be much more powerful. So that's a summary of this project. And what do we have there? Electron Ash enjoys writing OSD module in Verilog, wanted a bit far with it, so adding 4 bits Genesis MD style graphics, smooth scrolling, time map etc. That sounds like fun. Yeah, 4-bit actually in the original video, maybe I had 8-bit, or did I have 4-bit, not sure, but yeah, the problem is we don't have so much memory left. Old School brought a bunch of books teaching ways to make most of FPGAs, and learning can understand that book. So yeah, thanks for joining, and I hope to see you soon for the next videos and other software and hardware fun to come.